All right, let's talk through the banked curve problem. So this is kind of one of the, at the top of the food chain in terms of analyzing circular motion. And what we have here is that this is a car. It's kind of like a NASCAR driver, and he's coming around this bank, and he's got to go room, and he's going to go really fast, and he can go fast. Well, one, there is friction between the tires and the road, but the bank itself is going to help these drivers go fast enough and make the curve. Okay, so we have to think about all the physics involved in what's happening here, and I want to be clear that this is really just circular motion, and you have to understand that circular motion involves an inward force. And again, what direction is inward? You have to think about when the car's coming like this and going around the circle like this direction is inward. The car is making a circular motion like this. So this is the r hat direction. That's the inward direction. That's the important direction we're looking at. And then this direction is just the vertical direction. So we still have a y hat, which is up, and we have an r hat that's going to be going that way. And we're going to balance those two things. So as a car, when we come around this curve, vertically, we don't want any acceleration. We don't want to go up or down. And if we had a vertical acceleration, that means we'd be going somehow up the ramp or down the ramp. We want to maintain the same level on the ramp as we come around this circle. And so we want these to be balanced, and we want this guy, well, we need this guy to provide us with enough force to make us move in a circle. Again, there's a force that exists that makes you move in a circle. And so what we have to do is we have to break all these forces down. So let's draw a free body diagram and think about all the forces acting on us. And so we clearly have gravity. So we have mg that's down. And let's say we're going to go really, really fast. We're on the verge of slipping up the ramp. Again, if you were going to go really slow, well, you actually might slide down this ramp if it's steep enough. And so friction would go up the ramp. But let's say we're going to go fast. So we're looking for the maximum velocity. Well, if we're looking for the maximum velocity, then friction would help us. And so friction is going to go, if we don't want to slide up the ramp, friction is going to keep us down the ramp. Okay? So that's down the ramp with friction. And then we have the normal force, which is normal to the ramp. And those are the only three forces acting on us in terms of motion. Again, friction is going to prevent us from sliding up the ramp, so it's down, and the normal force, of course, is normal, and gravity is straight down. So the nice one, the easy one, is gravity, because it's straight down here, right? It's straight in the vertical direction. Both of these forces, though, well, we're going to have to break down the normal force and the force of friction. So I'm going to draw a ramp and just look at each one of those guys all by itself. Okay, so here's the ramp, there's theta, and I'm just going to look at the force of friction. The force of friction is down that way, okay? And we need to break it down. And what happens is friction is in and down. Okay, again, down the ramp is really inward and down. Okay, friction's going to hold us onto the ramp this way and push us inward that way. And we need to figure out which one's is cosine and which one is sine. And I just want to remind you, this is the angle of elevation. This is the angle of depression. Those angles are the same. And so this inward piece here is FF cosine theta. It's the adjacent piece. This one over here is FF sine theta. Okay, so we have that one broken down like we need it. Now we need to break down the normal force, and I'll draw a whole new ramp to try to keep this as clean as possible. So we have the same car, and now we have the normal force. Okay, there's the full-fledged normal force. But what does the normal force do? Well, the normal force has its own pieces. It's also pushing inward, and it's pushing up. It's got two pieces. And again, we need to figure out what those pieces are. But labeling it is the same thing. This is the angle with respect to the horizontal, and that is the same angle theta. But if that is some angle theta, then this is some new angle alpha. And look what, remember, the normal force and the ramp are perpendicular. So this red, that's theta. I'll label that. That little guy is theta. Then that means that's alpha. But if that's alpha, that means this guy up here has to be theta. But if that's theta, then this is n cosine theta. See how it's the adjacent to the angle? And then this inward force is n sine theta. And now we're good. Because what we can do now is we can look at the r hat. Again, I'm looking at F equals ma and F equals ma. This is going to be in the inward direction in the r hat, and this is going to be in the vertical direction. In the inward direction, what forces are inward? Well, the force of friction, cosine theta, that's pushing us in. And the normal force, but it's n sine theta, is pushing us in. And I'm going to add them together because they're both pushing in. There's no force that's pushing us outward, and that creates centripetal acceleration. Again, this net force causes us to move into a circle, and so we have that equation. And now vertically, we have the normal force is up. See how it's pushing us up? And that's n cosine theta. Friction is pushing us down, so it's a minus ff sine theta. And then, of course, we have gravity that was just straight down. There's no sines or cosines necessary. And again, we're moving around in a circle in the same plane, so we have no vertical acceleration. We have that equal to 0. Okay? And then the next step you would do when you're solving this equation is that we would then insert, instead of ff, we'd put mu times n. So we'd say mu n cosine theta minus n sine theta equals mv squared over r. And over here we would do the same thing. N cosine theta minus, instead of the force of friction, mu n sine theta minus mg equals to 0. And then the algebra takes over. Physics is done with the banked curve. We took the three forces, we broke the normal force. And again, if you just look at this picture, see how the normal force is going inward and up. The normal force is inward and up. The force of friction is inward and down. Inward and down. See how it's negative? And then gravity is down. The downs are balanced, and the two inward forces cause the centripetal acceleration. Okay, and so the next step algebraically, all I did was get rid of the force of friction by mu n. We're going to use this equation to solve for the normal force. Okay, so you would move that mg to the other side. I'm not doing anything right now. Oops, minus n sine theta just equals mg. And then I'm going to factor a normal force from those two things. Cosine theta minus mu sine theta equals mg. And then we know that the normal force equals mg all over cosine theta minus mu sine theta. Now this gets really messy, but I'm just going to take this value for the normal force and I'm going to put it up here. Okay, so I'm going to take this massive thing and throw it in here, and then I'm going to simplify that. So it's mu times this normal force, mg cosine theta minus mu sine theta times cosine theta minus that same thing, the normal force, mg cosine theta minus mu sine theta. That's the normal force, sine theta, and that all equals, oh, I'm going to run out of room here, mv squared over r. Whew. Okay, now you have to think about all this stuff can just kind of cancel, some things can factor, and realistically it just kind of gets a little messy, but those m's are going to go away. They all have an m. Okay, and then this denominator is really the same, and I could have factored that out right away if I wanted to, and I guess probably algebraically I should have, but this is just a mu g cosine theta, and this is just a minus g sine theta, and they're all over that same silly denominator. cosine theta minus mu sine theta, and that equaled v squared over r. So I would multiply both sides by r. So that just puts an r in the numerator, and then I would take a square root. And then I get v. That's the maximum velocity you can go. If you go any faster than that, and you're going to go off the ramp. Now the minimum velocity, we kind of have to redo some things, but not really. If we're going to go the minimum, the force of friction just points in the other direction. So instead of in and down, the force of friction would go this direction. It would go out and up. So all the force of frictions just change signs. That's actually going to be a negative, and then that's going to be a positive, because it's going to be up and out. So it's out and then up. So change those, but changing those just changes everything with a mu. So all you have to do is make that a negative and make that a positive, and then you have v min. So again, you can kind of trace that algebra, but again, v min is just going to put a negative sign there and a negative sign there, because it just flip-flops that vector completely. Okay, so that's the banked curve. Hopefully you followed along. The hardest part of the banked curve is drawing these pictures, and again, figuring out how to break down the normal force and the force of friction into the important directions. The important directions in this particular problem are the inward force, those forces, which cause circular motion, and then the vertical forces, which are just balanced because we're not actually sliding up or down the ramp.